So as I said, we need to prove graph contained in the union of ij. So to prove this inclusion, we take a point AFA in the graph. Take a point from the graph. Then, because the graph A is a point of U, okay? Therefore, there is and U is a subset of the rectangle I. Therefore, and the rectangle I is the union of the rectangle subrectangles from the partition P. So there is a subrectangle from the partition such that A is contained in J and U. Because A automatically belongs to U, but it has to belongs to some J. So for that J, A belongs to the intersection of J and U. Then the distance from A to AJ will not greater than the diameter of this J. But the diameter, according to the truth of our partition, all the subrectangle has diameter less than delta. Therefore, what's this AJ? This AJ is yes, this AJ is the taken here. At the AJ is this AJ we take before. Okay, so this is the AJ we take. So the distance from A to AJ is less than delta. So by the uniformly continuity of F, we have FAJ less than epsilon, which means FA belongs to the interval FAJ minus epsilon, FAJ plus epsilon. So A belongs to J. A belongs to J. FA belongs to this interval. So AFA belongs to J, Cartesian product of this interval. But this is precisely IJ. Okay, so we prove that every point in the graph of F contained in some IJ, contained in IJ for some J belonging to the partition P. So this proved the inclusion relation we need here. This proved this result, and this ended the proof of this example. Okay, so this example is quite interesting and important. Graph of continuous function has Jordan contained 0. Okay, so when we need Jordan contained 0, we introduce Jordan contained 0, the concept of Jordan contained 0, because we want to describe the integrability of some functions. So we have this theorem. F is a function defined on a rectangle, bounded. And so we have a rectangle I, and F is defined on this rectangle. But this I has a subset D. D is the subset of discontinuities of F. D is the subset of all the points where F is not continuous there. So the result is that if D has Jordan contained 0, then F is integrable over this rectangle. So this is an important theorem. It tells us that what kind of function is integrable. At the beginning of today's lecture, we have proved that continuous functions are integrable. But now, for functions which can be discontinuous at some point, if the point where the function is discontinuous is not too large, it has Jordan content 0, we can still prove that the function is integrable. Okay, so we prove this result. Given epsilon positive, because the D has Jordan content 0, this is our assumption. D has Jordan content 0. Therefore, we can find some rectangles the union of whose interior containing D and the total volume is very small. This is the third property of Jordan content 0 we discussed before. Okay, so there are rectangles I1, IM such that our D is contained in the union of this rectangle, of the interior of this rectangle, and the total volume of this rectangle is less than epsilon. Okay, so we have some rectangle containing this discontinuous point D. We have some rectangle whose interior containing this discontinuous point D. Okay, whose total volume is less than epsilon. So let E to be the rectangle removing the interior of all the II. Okay, so this E is bounded and closed. So E is the point here. The blue shadowed region is our E. This is our E. This E is a closed set. Of course, it is also bounded. Why this is closed? Because the interior of II are open. The union of all the interior of II is also open. This is an open set. So the rectangle I is closed. Removing an open set from a closed set gives you a closed set. So E is closed. And of course, E is bounded. So E is sequentially compiled. So F is a continuous function over E. Because all the discontinuous point of F contains in the union of II, which has been removed. So F is continuous over E. But E is sequentially compiled, therefore F is uniformly continuous. F is uniformly continuous on E. So for the epsilon given, there is a delta positive such that Fx minus Fy will not greater than epsilon for any xy from E whose distance less than delta. Okay. Now we want to prove that F is integrable, so we need to construct a particular partition of our rectangle I so that the difference between the upper sum and the lower sum is small. Okay, so we need to construct the partition. How to construct the partition? So we take a partition P is P1 Pn, a partition of I, of our rectangle I, such that the diameter of every subrectangle is small. For any subrectangle belonging to the partition. Okay? So we which the delta, we take a partition of the rectangle, so that every the diameter of every subrectangle is less than delta. This can be done. You divide the edges of I, each edge of I, k equally interval, and then when k is large enough, the diameter of the subrectangle will less than delta. Okay. So now, but this partition is not a partition we need. So we need to construct a new partition. How to construct a new partition? Let Pj start to be, maybe I will write it in next page. Let Pj start to be Pj union the I from 1 to n Aij Bij intersecting with Pj. A little complicated. What this means? So look at this picture. So the left picture, the black dot are partition. The horizontal black dot in the left picture are partition of the first edge of, are the points of the partition of the first edge of the partition P. Okay, and then that is the partition of the first edge of I of our rectangle is these 4 points. These 4 points are the partition of the first edge of our rectangle I. And then the blue here, the blue curve is the set D, and the green rectangles are the rectangle II. Whose the interior of their union contains the discontinuous point set D. Okay, so we add the definition of this Pj star. Pj star is the horizontal dots, no matter it is blue or red. That is the partition of the first edge of the rectangle obtained by adding some points to the partition of that edge from our original partition P. Okay, so this is Pj star. This is the partition of the GS edge. This is a partition of the GS edge of I. This partition of the GS edge of I is obtained from the previous original partition. We take diameter less than delta. We take a partition diameter less than delta. So for this partition, we add some point. What kind of point? Add those point. That is the end point of the rectangle II. So that is the red point in this picture. Okay. So this is a partition of the GS edge, a new partition of the GS edge of I. And then we take their product, denoted by P start. P start is P1 start, Pn start. So this is a partition of our rectangle I.